All right, if it cuts out again, I'm just going to have to go up and, I don't know what, do something else. All right, so if we take the vector function of the line, vector equation of the line, we can break it up, and now look at the two components, all right? These are the two components. The x component is x naught plus at, the y component is y naught plus at. These two equations are called the parametric equations of the line. All right, parametric equations. We said r naught was our initial vector, right? X naught, y naught, which was given to us by a point. The vector v was our direction vector, which we would have to calculate. But if we just replace the r naught right here and the v here, and then distribute and collect, we get this. Just using basic vector addition. When you do that, those two components are called your parametric equations. And the numbers a and b, all right, these numbers a and b are called the direction numbers of the line, because they give you the direction, right? Lastly, if you take this equation right here and you solve it for t, what would you do? To solve this for t, you'd subtract x naught, right? And then divide by a. Then over here, you'd subtract y naught and divide by b. And then they both be equal to t, wouldn't they? So you set them equal to each other. And what you get is this equation right here, which are called the symmetric equations. So there's basically right now three forms of a line. We have the vector equation, which is r of t equals r naught plus tv. We have the parametric equations, x equals x naught plus at, y equals y naught plus bt. And then we have the symmetric equations, x minus x naught over a equals y minus y naught over b. So you can see any of these forms, you should be comfortable with all three. Notice that on the symmetric equations, the number on the bottom here is the a and the b. That's always your direction, right? Direction vector. So if someone gives you the symmetric equation for a line, you could tell someone the direction of the line right away by just knowing those two numbers. Now, all of these concepts extend to three-dimensional space. So if we start with our initial vector, instead of it being x naught, y naught, it has to be x naught, y naught, z naught, right? And then our v, instead of it being two-dimensional vector, we call it ABC. Then the vector equation of the line becomes this instead. So it's still r naught, right? It's still tv. Then distribute the t and then collect it all together. And now we have how many parametric equations? Three, right? We have the three parametric equations. And we could solve each of them for t, couldn't we? And if we do that, you get three equations that you can set equal to each other. And these are called the symmetric equations for a line in three-dimensional space. Questions? All right, this is going to come up a little bit later, but let's talk about it now. If someone gives you the vector equation of a line, right back here, right here, this is the general vector equation of a line right here. It's just implied that t here is a scalar, and it can be any real number, which should draw the entire line, right? Both directions forever. Well, what if we don't want to draw the entire line? What if we just want to draw a line segment, but we still want to use the vector equation? Then here's how we do it. This is the one I like the most. You can do it this way, or you can do it this way. This is the one that I think you should go with. Remember, we're starting at r naught, right? Let's say we want to go to r naught, and we want to stop at r1. So in the picture, here's what I'm saying. Let's say that we have a line segment like this. I'll call this point x naught, y naught. Call this one x1, y1, like that. Now if I throw my axes in here, we call this vector what? R naught. And we called the vector that went here to here R1, didn't we? If I just want to draw this line segment, right, and I don't want to go forever, how could I draw this point right here? Just this point. How could I draw that? By drawing just what vector? What's the vector that would get me just to here? R0, right? What would I need to get me from here, from the origin all the way to the last point? I would need to go R0, right? Plus what? V, right? Plus V. So that would get me here. This one gets me here. Y'all follow? How would I get to the point right in the middle of them? I'd add half of V, wouldn't I? Instead of going the whole V, I'd go half of V. What if I wanted to get a quarter of the way? Right, like somewhere in here. Again, I wouldn't do R0 plus the whole V, I would just do R0 plus a quarter of V. And how would I get all the points in between? My multiples, all the points that lie on that yellow right there. Okay, the t, right, the scalar that we're using, the t would have to be between 0 and 1. Because if t was 0, isn't that what this is right here? I'm adding 0 v's to it. And here I'm adding, what, 1 v to it. And then here I'm adding half of a v. And if I want everything in between, I need to let that t go between 0 and 1, don't I? And that'll give me just the stuff between them. Does that make sense? So back over here, that's what this formula is saying, this second one. If you have two vectors, right, R0, R1, you want to draw the line segment between those vectors, you will go R0 plus T. What's R1 minus R0? That's V, isn't it? This is R0 plus TV, but your T is now restricted between 0 and 1. So if you want to, take this and modify the formula and make it this instead. R of T equals R0 plus TV, but T is between 0 and 1. That will always work, okay? That will always draw the vector, the segment between the two. If you change this, to 0 to 2, you're no longer going to draw the line segment. It'll be a line segment, but it won't be the one between the 2 points. All right, I hope that all makes sense. All right, so the points 3, 6, and 7, 4 lie on a line. Find the vector equation of this line. Find another point on the line. Find the parametric equation of the line. Find the symmetric equation of the line. That one, I'll let you do. Let's do the next example, which is in 3 space. Right? This is 3-dimensional. It's a little more interesting. I don't want to get ahead of myself, but it seems like this is holding up a little better, doesn't it? I might have a bad cable there. All right, so we're given points, aren't we? Let's not confuse points with vectors. What I'd like to do is find the vector equation of this line. So for me and for you, as soon as you see vector equation of a line, you should be thinking this. So we need R0, right? So what is R0 going to be here? What's that? Okay, which means it could just be the first point converted to a vector, right? Could I have used the other point? Yes. It doesn't matter. R0's always just some point on the line converted to a vector. So I'll use the first one there, 3, 6, -4. Everyone understand that? That's just one of the points. Now all I need is V. V is the vector that goes from R0 to R1, right? Subtract vector connecting these two. Now, does it really matter which one I subtract? You think about the picture visually. V was a vector connecting the two, right? But didn't we scale it by t, and t was any real number? So we wanted to get all scalar multiples. So it wouldn't have mattered, would it? If I would have gone back to this picture, the first picture, this right here, I could have pointed it in the other direction, right? It could have been this one. And then when I take all scalar multiples, I'm going to go in both directions anyway, so I'm going to get the whole line, right? But I'm going to stick with what I've been doing here, which is V will always be the one that connects R0 to R1, right? So I'll label these up here just so we stay with the same convention. Oh, no. What in the world is going on today? It's like my stylus isn't working now. My God. I don't know what to tell everyone right now. See if you can work that one out. Get your V. What's your V? Which is? See if you can work it out. Work it out. Give me a minute to do this. Everything there I think you can follow through with, right? Find your V. That's your vector equation. I'm going to see if I can bring this thing back to life. It's back. What's V? 4, 8, -3. Right? So the vector equation of the line, right here, I'm ready to write it down, is R of t equals R0, 3, 6, -4. For this last component right here, you're doing -7 take away -4, right? So double negative. T times 4, 8, -3. And now what I'm going to do is I'm going to distribute the t through, right? And then add these two together. If I do that, what will my first component be? What is it? Oh, 4t plus 3. I thought I said 14. Okay. You said 4t, right? All right. So you go 4t plus 3 or 3 plus 4t. It doesn't matter, right? Either way? I don't care. I've always written it, and most books write it that way, so that's the way I'm going to write it. The next one would be 6 plus 8t. And then -4 minus 3t, where t is an element of the real numbers. This is the vector equation of the line connecting those 2 points together. That's the answer to part A. So what about part B? Find the parametric equations of this line. So all you have to do for parametric equations is write down x, y, z, and just write down the components, right? The components are 3 plus 4t. The next one, 6 plus 8t. The next one, -4 minus 3t. That's your answer for part B. Again, t is a real number here, right? T is any real number. Part C, find the symmetric equations of the line. So how do you find the symmetric equation? Solve each of these for t, right? And then set them equal to each other. So I would subtract 3 and divide by 4. So my first one is x minus 3 over 4. But that's going to be equal to the next equation solve for t. So subtract 6, divide by 8. Y minus 6 divided by 8. And then on the last one to solve for t, it'll be z plus 4 divided by negative 3. So z plus 4 divided by negative 3. Symmetric equation. How is it that the symmetric equations work? Like, you know, I mean, like here, if I said, give me a point on the line, right? You could just plug in any value you want for t, right? And that would give you a point on the line, right here. Now, what about up here? If I said plug in a value of t, it would spit back a vector, wouldn't it? But that vector would correspond to a point on the line. So it's very easy from these two versions to just start spitting off the different points of the line, right? So how does the symmetric equation work? That's right. This is how we can check to see if a point does exist on the line. So like, for example, does 0, 0, 0 live on this line? Does the origin live here? If I plug in 0 for x, 0 for y, 0 for z, these all need to be true. These all need to be equal to each other. So I don't think it would, right? Negative 3/4, if I plug in 0 for x, that's not negative 3/4. Or is it? It is. What about 0 here? That's not right. So 0, 0, 0 would not work. Make sense? Okay. Does this point live on our line? 3, 6, negative 4. Plug it in here. 3 gives me 0, 6, 0, negative 4, 0. So 0, 0, 0. They're all equal, so that would work. Does that kind of make sense to you? Okay. This one isn't used that much, but I just want you to see where its value is. Like you could just check real quick if it exists, if a point exists or not. All right, now the last thing, find where this line intersects the YZ plane. Where does this line intersect the YZ plane? YZ plane means your x is 0, right? So for part D, YZ plane implies that your x has to be 0. So how does that help us? What can I do? Set x to 0 in C. So you could do that and solve for y and do that. Okay, that would work. Any other ideas? Set x equal to 0 in B and solve for t. And wouldn't you know exactly what t is? Right? And then you would know exactly, if you know what t is, you know what y is, and then you would know what z is. That's the way we'll do it. So we're going to go into the parametric equations. We're going to rewrite the parametric equation x equals 3 plus 4t. We're going to replace x with 0. And that gives me 3 plus 4t is 0, which means t is negative 3/4, right? Once I know what t is, I can now go again to the parametric equations and solve for y and z. So this implies that y must equal 6 plus 8 times negative 3/4. So that's 6 minus 6, so that's 0. And then we also know that z must be what? Plug in negative 4 minus 3 times negative 3/4, right? So negative 4 plus 9/4, which is what? Negative 7/4. Just careful with your negatives. So what's the point? 0, 0, negative 7/4. It actually lies on the z-axis, doesn't it? It just so happens to lie on the z-axis. You won't always have 0, 0 for two of them. I mean, think about this. I mean, I think that this is we've done a lot here. If I give you 2 points in three-dimensional space, right? There's a line going through them. You should be able to tell me exactly where that hits a certain plane. That'd be hard to do, just geometrically drawing things and trying to figure out where it hits that plane. Without all the vector stuff, I guess it would be a bit of a challenge. All right, let's move along. All right, determine that these lines are what we call skew. That is, that they do not intersect, they are not parallel, and they are not orthogonal. So we have two lines. Do these lines live in two- or three-dimensional space? Three-dimensional space, because there's three components. Now, notice I put L1 here. You could have put R of t equals, and then here's the vector equation of the line. And then on this one, notice I use a different variable. I use S instead of t. Why do you think that is? It's a different line, so I'm trying to keep them distinct from each other. So the S here is just like the t was before. S is just a real number. So if I have two lines in three-dimensional space, to be skew means they're not parallel, they are not orthogonal, and they don't intersect. So how can we show that? Let's start with the fact that I think the hardest part is let's show that they don't intersect. How could we show that they don't intersect? What's that? Set what equal to each other? You're on the right track. Because we're given the vector equation, so we're given the components. Would you agree that if they are equal to each other, then there's some vector that's exactly the same for both, right? Remember, the vector goes from the origin to some point on the line. If they intersect, then there's a vector off both of these that go to the same place. Which means that if the vectors are the same, the components are the same, aren't they? That's what it meant for two vectors to be equal. They have the same components. So what I need to do is set the components equal to each other, right? Now do you see why I didn't have t for both? Right? Here's a way of looking at it. I hope this will help. And again, I have to do it here in class. I can't do it on my computer. Let's say the ruler here is the first line, okay? As t changes, I'm moving along the line, right? As t changes. So let's say here's t is 0, right? Let's say right here is t is 1. Let's say at the end of it is t is 2, all right? So t is 1 is right here. Let's say that this line intersects it. Now, there's some vector that goes to both, right? We know at t is 1, we're going to be at their intersection. But on this line, if I say t, then t equals 1 might be down here. And t equals 5.6 might be where they hit each other. Does that make sense? The t does not have to be the same for both. That's why we're calling one t and one s. Huh? Okay. You're moving along one line. The variable is t. There's some t that corresponds to that point of intersection. The t that corresponds to that point of intersection on this line does not necessarily have to be the t that corresponds to that point of intersection on this line. So we call the first one t, we call the second one s. Because I can almost guarantee you, if you called these both t's, that you wouldn't be able to find it. It wouldn't exist, but there would still be a point of intersection. Okay, so let's set these equal. 1 plus t must equal 2s, right? So I have one equation, how many variables? Right there. 2? Okay, that's not enough to solve. So now I go to the next one, right? Negative 2 plus 3t equals 3s. 3 plus s. Now I have two equations, right? In one variable. Two equations in two variables. Is that enough to find a unique solution? Yes. So I'm not even going to worry about the third one yet. All right? I'm just going to try and get a unique solution here. So I'm setting this up as a system of equations. I'll solve the first one for t. I'm going to use substitution here. I know I could do like a matrix and stuff, but this looks like a pretty easy substitution. Solve the first one for t. Take that and plug it into the second one, right? So the second equation becomes negative 2 plus 3 times t, which was 2s minus 1, and then equals 3 plus s. Everyone follow what I'm doing here? Okay, now distribute through. Negative 2 plus 6s minus 3 equals 3 plus s. Let's get all the numbers to the right side. So we got 8 over there. 8 equals 5s. So s is what? 8/5. Did y'all get that too? Y'all agree with that? Now once I know what s is, I can go get t, right? So to get t now, t is equal to 2 times 8/5, take away 1. T equals 16/5, take away 1, which is 11/5, right? According to what we've done right now, it looks like on that first line, if t is 11/5, so you start the clock and it starts drawing the line, you stop it at 11/5, that point right there, looks like it might correspond to the other line when you let s go and you go to 8/5, and that's where they look like they intersect. But they don't. Because, what? Why don't they? That's right. We've only looked at the x and y components. For the intersection to occur, we also need that third component to come along with us and match also, right? So what I'm going to do is I'm going to go to this third component, and I'm going to plug in the t I just got, and I'm going to plug in the s I just got, and I'm going to see if they work, right? That third component has to be equal for these to have the same vector. So let me replace that 4, make it 4 minus 11/5, which is, what, 9/5, right? I need this one to be the same thing when I plug in 8/5 for s. Is it? Let's see, negative 3 plus 32/5, 17/5. These two are not the same, right? So I got my first two components to be the same, but I couldn't get my third one to be the same. Is that enough to show that they don't intersect? Yeah, because look, this t value and this s value are the only ones that make these two work, right? They're the only ones. So I could even try and figure out something from this, but ultimately, this is the t and the s that would make these two work. So we can say for now they don't intersect, right? We okay with that? All right. What's the next thing we wanted? Okay, show that they are not parallel. Show that they are not parallel. How can I do that? Okay, I think I agree. Both of these lines have a direction, don't they? The v Like each of them had that v vector, which was the direction of the line. Yes? Parallel lines have to be scalar multiples of one another, right? Which means their directions would have to be multiples of one another. So what is the direction vector of this first line? And I will call it V1. Does that make sense? To call it V1? The direction of that first line? What is it? 1, 3, negative 1. It comes from the coefficients on t, right? The numbers in front of t, y'all saw those? 1, 3, and negative 1. Those give you the direction of the line. So 1, 3, negative 1. And what's the direction of the other line? 2, yeah, 2, 1, 4. Again, coming from 2, then the 1 in front of the S, and then the 4 in front of the S. Are those parallel vectors? How do we check to see if two vectors are parallel? See if they're scalar multiples, right? But I showed you there was a real quick, easy way to do it. Do you remember? Take the ratio of the components and see if they're the same ratio. So like, look at that first vector. Make a fraction, 1/2. What does the ratio of the next one need to be? 1/2 again. And it's not, right? It's 3. And the ratio of the last one's negative 1/4. So if the ratios are not the same, they're not parallel. Do you remember that? Okay. The other way to do it is just to look at it and try and see if one of them is a multiple of the other. Right? What we're trying to check is V1 some scalar multiple of V2? Right? That's what we're asking. But you'd have to see what the C2 is. No. That's not what we're doing there. What else could you check? What's another thing you could do? Two vectors are parallel if and only if? That's right. The cross product is 0. So you could have taken the cross product of those two vectors and saw that it was a non-zero vector, and you'd be done. So there's a couple of different ways to do that. I think just looking at them and seeing common ratio isn't there, you're done. All right, that shows that they're not parallel. How do we show they're not orthogonal? How do we show they're not perpendicular? Dot product what? Yeah, dot product their directions, right? If they're perpendicular, then the direction vectors are perpendicular. So our standard check for orthogonality with vectors is dot product. What is the dot product of those two vectors? It's a number, right? It's the number 2 plus 3 minus a fourth, which is not 0, right? So all I did was, remember how we dot, right? Multiply and add, multiply and add, multiply and add. That's not 0. Dot product's not 0, therefore not perpendicular. So it's skew. Those two lines are skew. They don't hit each other, they're not parallel, and they're not orthogonal. That's right. If the cross product is the 0 vector, then they're parallel. All right. That's the easy part, lines. Now planes. So when we talk about planes, we've already talked about some important ones, right? The XY plane, the YZ plane, the XZ plane, right? Those were our coordinate planes that we used to kind of break up three-dimensional space into the different octants. But we stayed away from tilting the planes over and giving them some sort of angle, right? We've kind of stayed away from it. But, oh no, we had that one tetrahedron bonus problem, right? Where you had we did it in the room, where you connected those points and we tried to find the area of that one. That was a bonus. So what we want to talk about now is just general planes in three-dimensional space. Sheets that extend in every direction forever, and what their equations are. So equations of a plane in three-dimensional space. We've seen that to define the vector equation of a line, right, we needed what? At least a point on the line and its direction vector, right, R naught and V, or 2 points, right? If we're given 2 points, we have to create the V, don't we? We have to actually compute what V is. Isn't that just like in college algebra? Define a line, we need 2 points, or a point and a slope. Now the slope is like the direction vector. That's what it is for us now. Now we're going to focus on defining a plane. We can see below that to clearly define a plane, we would need 3 distinct points. So I'm going to just do this. I'm going to set it up and see if you can follow this. All right, everyone see this plane that those 3 points pass through? You'll see it? Okay. Looking at it from the side there. Here's how we're going to come up with the a way of defining it. First of all, we're going to create vectors that go from the origin to those 3 points, right? We've got vectors. So for each of those points, we now kind of convert them to vectors. And that's what we would get. Then from the tip of one vector, I'm going to create vectors that go to the other 2 tips, right? So now we have these 2 red vectors. I'm going to take the other vectors out of there so we're not confused. Those 2 vectors lie on that plane, right? Don't they? Now, if we take the cross product of those 2 vectors, we should get a vector that pops out of the plane, and it should be orthogonal to the plane, shouldn't it? We talked about that last class, the orthogonality of the cross product. And now I'm going to take those 2 normal vectors off. All right, see the picture? Now, let's go back up here. Notice that if we cross the vectors, we get that orthogonal vector. We call that the normal vector for the plane. We call it the normal vector. So as it turns out, that in three-dimensional space, if we want to define a plane, we need 2 things and only 2 things. We need a single point on the plane, and we need any normal vector to the plane. Of course, if you have 3 points, that defines a plane, doesn't it? 3 points define a plane. But with us, what we want is just 1 point and a vector that is perpendicular to the plane. And think about it. If this is, if I just take a plane, right, fix it somewhere, like let's say right there, if I know 1 point on it, and I know this vector here, that should define the entire plane. There is only one plane that is orthogonal to this vector and goes through that point. There's only one. Do y'all believe that? Like if you try and tilt this a little bit, right, then you're no longer orthogonal to the plane. So this one's got to tilt over also. Now, having the point's important though, right? Because if I take this vector's orthogonal to this plane, if I move this plane up and down, that vector is still orthogonal to all those planes, right? So that's why we need the point to say, okay, right there, stop. That's the plane I'm talking about. So with the combination of just those 2 pieces, we will define the plane uniquely. All right, so if we're given a point on the plane, right, and we're given n, the vector n, which we will call the vector, we will give its components the variables a, b, c. If n is any normal vector to the plane, any, so it can point out the top, the bottom, it can be, really long or really short. As long as it's orthogonal to the plane, then the equation of the plane is this. A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And I point out here, notice, this is not a vector equation. Do you see any vectors in that notation? No. It's your standard plane equation. In college algebra, you probably solved systems of linear equations where you had 3 equations and 3 unknowns? Do I remember ever seeing something like this? X plus y plus z equals 10. 2x plus y minus z equals 4, right? Something like this. 3 equations, 3 unknowns. Geometrically, this is the intersection of 3 planes. That's what it was. That's what the geometric solution to this is. So each one of these were planes, right? Well, notice you have a number in front of x, a number in front of y, a number in front of z, and then a number by itself, right? That's the equation of a plane. That's exactly what I'm saying here. You have a number in front of x minus, now x naught is a number, right, because it's a point on your plane. And then y minus y naught's a number, this is a number. If you distribute the a through, you distribute the b through, you distribute the c through, you'll have x, y, z, right? And you'll have some constant. That's what I say here. Distributing through, get ax plus by plus zz plus all of these together. This is just a number. So we give this number right here, all this together, we give it a unique variable. We call it d. And so this becomes our general linear equation of a plane. But look at this. Look what is so important about the linear equation of a plane. The a, the b, and the c are what? They're not just like random numbers. I mean, these are very important numbers. What does the a, b, and c tell us? It's the normal vector, right? The a, b, c are the components of the normal vector. They will always be the components of the normal vector, right? Go back up here, right? A, B, and C. A, B, C is the normal vector. So if you look at the equation plane right here, you should be able to say where the normal vector is pointing. Going back to this, look at this plane right here. What's its normal vector? What's the normal vector of this plane? 1, 1, 1. What's the normal vector of this plane? 2, 1, negative 1. What's the normal vector of this plane? Negative 1, 1, 4. There's a lot of information here that we may or may not have known before when we just looked at these. We have a lot to go with. Once someone writes it like that, we've got a lot of information that we can use to solve some problems, all right? All right, let's find the equation of the plane if we're given 3 points. Again, let's appreciate what we're doing here. Someone gives us 3 points in 3-dimensional space. It defines a plane. What's that plane's equation? So here we go. The points are 1, 2, 14. The other one, -2, -5, -1. The other one, 12, -3, 1. Any ideas how we can do this? Okay, so there's my plane. What do you want to do? Create 2 vectors here. Cross them. That'll give you your n. And then all you need after that is a point on the plane, which we have 3. So we can pick any of them, right? So I'm going to write this down a little bit. I want 2 things. I want a x naught, y naught, z naught, right? And I also want a normal vector. Right, those are the 2 things I want. If I get those, I can write the equation of the plane. So the x naught, y naught, z naught, I think, would you agree that's the easiest part? Which point would you like to use? First one? Okay, so it's the vector 1, 2, 14. Okay, done with that part. Now, let's get our normal vector. So how do we get our normal vector? You said create 2 vectors first, right? So how about we go, we'll call this point here, this point here, this point here. How about this vector? What would that vector be? I'll call it U. What is it? -3, -7, -15. All agree? The vector from that point to that point. How about V down here? What's this vector? 11, -5, -13. Yes? Then what's N? N will be the cross product of U and V, which we've learned to do them by hand, right? But we've also learned to do them on the calculator yet, or no? Anyone learn on your calculator yet? What? What are y'all waiting for? It takes way too much time to do it by hand sometimes. So I will do it by hand. IJK, only because I don't have my calculator with me. I thought everyone was going to come in here, but oh, I could do it. Well, it can be lazy when, you know, you're asked to do like 12 plus 17 and you're like, hold on. You know, that's just not even thinking. I want you to use a calculator because you'll waste time on the test if you do it by hand. Yeah. Yeah. So remember how to do this, right? We cover up this and then we do here, 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 here. What's wrong? The thing is, you can't use Wolfram alpha. Someone give me the vectors here. Cross product. What are the vectors I'm crossing? Let's double check. That look right? -3, -7, -15, 11, -5, -13. Okay. I don't know if my syntax is correct here. Oh yeah, Wolfram alpha knows. Look at that. It even generates a three-dimensional picture of that cross product. That's pretty cool. Here it is though. It's the vector 16, -204, 92. 16, -204, 92. 16, -204, 92. And so we have everything we need, right, to write the equation? The equation of a plane is A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught, equals 0. So my A is what? What's my A? 16 times x minus, what's my x naught? 1. Plus B, but it's negative, so -204, y minus 2, plus C, so plus 92, z minus 14, right? Equals 0. Now that is the equation of the plane, and that's actually acceptable on a test to leave it like that, unless I specify that you need to go further. But to go further means just distribute 16, distribute the -204, distribute 92, and you see you'll get a number, right? And then all the other stuff will just be a number. It'll be what? 16x minus 204y plus 92z, and then you'll have some number out there. And you can leave the number on this side. This is kind of important, though. If you leave the number on this side, on the left side, that's D. If you take it to the other side, it's -D. All right, so D is what you get when that number's on the left side. -D is when you take it to the other side. All right, that's it for that. So now, let's talk about some other things with planes. If we have two planes, right? I'm going to try and tilt these to the side. Let me see if I can find it. Where is it? There it is. Like that. So what I'm trying to do is get two planes and they hit each other. I'm trying to turn it so you're looking at it like that, right? From the side. So if two planes hit each other, we're interested in knowing what the angle between them is, right? The angle between them. So just look at the normal vectors for each of these planes. Look at the normal vectors. And if I move the normals to their line of intersection, so those two planes hit it at a line, right? Two planes will intersect at this line. If I move their normals, because the normals are vectors, right? So I can slide them around. If I move them down to that intersection point, I hope you can tell that the angle between the two normals is also the angle between the planes. Why would that be true? Because the normals are perpendicular to the plane, so they're off by 90 degrees, right? So the normal of this wall is this, right? And the normal of the floor is this. So what's the angle between the normals here? 90, which is the angle between the floor and the wall anyway, right? So it makes sense that the angle between two planes would be just the angle between the normals. All right, so if that's true, then two planes are parallel if and only if the normal vectors are scalar multiples, right? There's your normal vectors. They're pointing exactly the same direction. That means, well, they're not pointing the same direction necessarily, but they're scalar multiples. One could be pointed out the other side. So parallel planes, normals are parallel. And what if the planes are orthogonal? That's right. Yeah. So if you have two planes and you're saying, are they orthogonal? You can take their normal vectors and dot them and see if it's 0. Find the angle between these planes. How do we find the angle between the planes then? P1 is x plus y plus z equals 5. I think it was that cable, don't you? That's good, because I don't want to have to replace this laptop. Thank you. I'll let you think about that while I hand stuff back. See if you can figure this out, the angle between them. Y'all can talk to each other. No, if someone asked you here, what's D, you would say -10. What? Is that what you said? The negative D is positive D. The negative, no, -10 is positive D. Yes, that is correct. All right. That's right. Correct. Okay. Now look, I'm handing back your first quiz. This is just to get an idea of how I grade and you know my expectations. So if you have anything on here that I hand back to you that you're like, why did he take off so much? Just come talk to me, all right? We'll sit down and I'll explain what I'm looking for. Jose? Okay. Aguilar? Oh, okay. Alexandra? Allie? No, Allie, right? Okay. I can't fold that. Jose. Mark? Thomas? Diego? I have one with no name, and they stapled the test to the quiz to the first page, and then that's the writing right there. So you can come, if you don't get yours, you can come look at it. Dan, Patrick? Roll. If yours is the one with no name, I haven't put the grade in, obviously. Uh-oh. Yeah. How do you say it? Angel. Okay, so I'll say okay. Thank you. Okay. Tomorrow? Joshua Shaw? Joshua Shaw? No? Jason? That's all I had. If you turned in and I didn't hand back, then I don't know where it is. Can you put your name, give it back to me? All right. All right, just set it right here. Thank you. All right, we get anywhere with this? What's the idea here? What do you do? Okay. So what are the normal vectors for these two planes then? So, yes, the coefficients of the corresponding variables. So the normal vector of the first plane would be 1, 1, 1, right? Corresponding coefficients here. 2, negative 4, 7. And now this problem really just reduces to what's the angle between two vectors, right? What's the angle between two vectors? So we had a formula for that. The angle between two vectors. The angle between two vectors is the magnitude. And then if you solve that one for the angle, you get arc cosine of the dot product over the magnitudes. Good, yes. So it's that formula solved for theta. Okay, so we know that the angle between will be arc cosine of, in this case, n1 dotted with n2 over magnitude of n1, magnitude of n2. Whatever that is. Anyone get that yet? Arc cosine, what's their dot? 5? Dot product 5? Okay. What's the magnitude of n1? Square root of 3, right? You do 1 squared plus 1 squared plus 1 squared, then square root. What's the magnitude of n2? Is 79 under there? Okay. And now just someone on their calculator figure out what that is. For the angle, you're in degrees. See if someone else gets 69.7. Not that I don't trust you, but I don't trust you, no. But we should at least get two people to agree, right, before we say something's right? Okay, all right. So we happy with that? That's the angle between. And remember, that's the smallest angle, right? That's the smallest angle. Your answer should always be between 0 and 90 degrees. Yes, because it always returns the smallest angle. So if oh wait, did I say no? Between 0 and 180. Sorry. Yeah, it's always the smallest, because if you go past 180, it'll be this one instead of the one on the bottom there. Okay. Acute, yeah. So in this case, it will be smaller. Because it's, when you think about a plane where planes intersect, look, if these are two planes you're looking at from the side, you have to have an acute angle. But in terms of vectors, so forget the planes. If you have two vectors, then it can be between 0 and 1. But with planes, it's always going to be that smallest one. So Which ones? Which ones? These complementary? Alternate interior. But isn't complementary angles add up to 90? Supplementary. There you go. Okay. That's why I was okay. That's why I wasn't sure which one. These two would be complementary, yeah. I mean supplementary. Yes. All right. I don't know if we want to go through the attic and start pulling things like that out. I always remembered complementary and supplementary, that supplementary has two P's. So double. Yeah, did what? It's weird how everyone kind of finds their own little things that they use, right? 69.7? What? 0.7 degrees. Make sure you're in degree mode on your calculator. Okay. Now, a really big result here. If you have two planes, they intersect, and they're not parallel, right? So they're not like the roof of this room and the floor. They're not parallel. They've got to hit each other, right? Somewhere then. And no matter what, they're going to hit each other in a line. Where they hit will be a line. That line extends in every direction forever, right? Since it's a line, can't we find the equation of it? Sure. What do we need to find the equation of a line? We need, what do we need to define a line? A point and, or 2 points, or a point and a direction vector, right? Okay. Now, look at this blue line here. Can y'all see that blue line in there? Okay. Watch how I'm going to look at the normals for each of the planes. So can you see that the green one is the normal vector for this plane? Right there, right? It's orthogonal. And then the red vector is the normal vector for this plane right here. Yes? Now what I'm going to do is I'm going to move those normals, sliding them so that they slide down to the line of intersection where they hit each other. Now, these two vectors right now, they look orthogonal, but they don't have to be, right? Because the planes are hitting each other. The normals don't have to be orthogonal. But check this out. If I cross these two vectors, what's it going to give me? A vector orthogonal to both, right? Does it make sense to you that their cross product would have to live on that line? Does that make sense? If, you know, I'm having two vectors here, I mean two planes like this, right? Then the normal vector for that plane's here. The normal vector for the other one was like this, right? And I'll just kind of, I'll change them like that, right? If I move them tail to tail, right? And cross them, right-hand rule, I come out like this, right? That vector is my right-hand rule. That vector is on the blue line. So guess what that vector is? Or what can it be used as? What part of our vector equation for a line? That's the direction vector, isn't it? We can use that vector as the direction of our line. And then all we would need then is what? A point. And that point would be any point that lives on the intersection of the two planes. So, back it all up. We have two planes, and we want to find the line of intersection. We find two things. We find any point of intersection, so any x, y, and z that satisfy both equations at the same time, and then we take the normals and we cross them, and that's our direction vector. Did this help at all to see it like this? I may have said this in the beginning of this class, that one of the things that I've always thought was challenging in Calculus 3 was the visualization of it. You know, so I hope this helps. I just stand up here with pieces of paper and try and make it make sense like that. Or I try and draw it on the board and you try and copy me and see if you can draw it too. All right, find this vector equation of the line of intersection. This right here is a fundamental concept in this class, right here. You have to be able to find the vector equation of the line of intersection of two planes. All right, let me write the planes down first. I have P1 is the plane x plus y plus z equals 5. Plane 2 is 2x minus 4y plus 7z. Are those the same two planes that we had a little while ago? Yes? All right, so what we need, right, what we need is a point. That point will come from x naught, y naught, z naught, right? It's going to come from the vector, x naught, y naught, z naught. But that's actually just any point that lives on both those planes, right? Any point. We also need n, don't we? How are we going to get n? I mean, not n, sorry. Hold on. I just had complete brain fart. Hold on. We want this, right? Pardon. This is what we want. I forgot what we were trying to find. For a second there, I thought we were finding the equation of a plane. We're trying to find the equation of a line, right? We want this. We need a point so that we can get R naught, right? That's what we're trying to get, R naught, which will just be a point that is on both of these planes. Then what else do we need? Not n. We need v. But v will be what? The cross product of the normal vectors of those planes, right? Which I will call n1 and n2. N1 is the normal vector of plane 1, n2 is the normal vector of plane 2. Any questions on what I'm looking for? All right, let's find, you want to try and find R naught first? No, you want to do V? V seems easier, right? I'm going to do IJK. Going to be doing cross product on what vectors? 1, 1, 1, 2, negative 4, 7, right? Do your cross real quick on that. Oh, bless. What was it? 2, negative 4, 7? (11, negative 5, negative 6). Okay, that's our V. And any questions on where V came from? All right, now the point. We're going to have to find an x, a y, and a z that simultaneously solve this system of equations. We have 2 equations and 3 unknowns, so there's an infinite number of answers, right? Well, it's a line. It should, right? The intersection should have an infinite number. So let's do what we had done once before when we were trying to find the equation when we had too many variables. Just let one of them be something like, why don't we let z be 0, right? And see if we can find an x and a y that work. So for my point, going to let z be 0. I could let x be 0, right? I could let y be 0. If z is 0, I get x plus y is 5, and I get 2x minus 4y is, can I just move that negative 10 over and make it 10? This is a new system of equations. I'm going to solve this one using elimination instead of substitution. Is that really going to be what I think it's going to be? So all I did, I multiplied the first equation by negative 2. And now I'm going to add down. When I add down, I get, yes? One. Remember on the J for the cross, you have to switch the sign all the time? Did you do that part? Let's see. When we do J, we do 1 times 7, which is 7. Take away 2, which is 5, but then change the sign for J. So negative 5. What do we get here? Y is 0, right? It's negative 6y equals 0. So y is 0. If y is 0, then what's x? 5. So it looks like 5, 0, 0 is a point that lives on both of them. Agreed? You could also just double check, go back up to the beginning, replace both y and z with 0. Y and z with 0, and yes, x is 5 in both equations, so that works. So are we ready for the vector equation of the line of intersection of these two planes? It is r of t equals r naught, which is any point on the line written as a vector, so 5, 0, 0, plus t times v, where v is the direction vector, but v came from the cross product of the two normals of the planes. So it was the vector 11, negative 5, negative 6. Which if I write this out, 5 plus 11t, negative 5t, negative 6t. T is a real number. It draws the whole line. Okay. You don't, I'm okay with it. But now if it's a line segment, you do need to show the restriction. We'll just assume t is a real number unless otherwise, you know what I'm saying? All right, we still have about 8 minutes. Y'all okay? Let's see if we can just finish this off. We've got 2 more little concepts to look at. All right. This is a big deal, I think, this one right here. If you have a plane sitting in 3-dimensional space, right, and you have a point in 3-dimensional space, you can find the shortest distance between that point and that plane. So like the projector, right? There's a shortest distance between the projector and the ground. It would just be the distance straight down, wouldn't it? Straight down to the ground? But if you tilt everything now, and the plane can be any plane, now the shortest distance is harder to find, isn't it? Because it's not straight down. So how do we do it? So given a point, someone has to give you a point, we're going to call it x1, y1, z1, and they give you some plane, so it has a plane equation, ax plus bx plus by plus cz plus d is 0. We can find the shortest distance between them by first choosing a point on the plane. Then so let's act like we didn't have a visual for this. So all you have to do is take a point on the plane, okay? You have the point, let's say the projector is a point, we got a plane here. Take a point here. Next we find a vector from the point on the plane to the given point, so a vector from here to there. We'll call that B. And then we take the normal vector of the plane, that's N. And then it's obvious, right, that if we take the component of the B vector onto the N, then that would be the shortest distance, right? No, that doesn't make any sense. So here, there's our point, right? There's a point, there's a plane, right? That's what we want. Now, we just pick any point on the plane. So I pick just an arbitrary, whoa, that's not on the plane. Let's act like it is. I think it's just a mistake on my input. So let's just act like that's on the plane, right? Now, we are going to generate from that point up to that point a vector. We can do that, right? 2 points, you can create the vector pretty easily. How hard is it going to be to get a point on the plane? You just have to find any x, y, and z that satisfy the plane equation, right? So that should be pretty easy to do also. Plug in numbers till you get something to work. Then we have a normal vector for the plane, don't we? That normal vector does not need to go through that point, right? The point I'm trying to find, it does not need to go through that, right? The normal can be anywhere. But because it's a vector, I could slide it to where it points straight up to that point, can't I? Then I'm going to shift the blue vector over, because it's a vector, I'm going to shift it, right? And forget that first one was there, right? And then I'm going to drop a perpendicular. Remember how we talked about projection vectors is like dropping a perpendicular? So if I project the blue onto the red, the projection, that length is the distance, isn't it, that we're trying to get? So this is the length of the projection vector. Isn't the length of the projection vector the component? Remember there was two calculations. We had the projection, PROJ, of something onto something. Then we had the comp, COMP. Isn't that black the component of B onto N? N's the normal. B is the vector that we created very easily. We do that computation and we're there. Now does that make sense? Now we take the magnitude, because we learned last time component could be negative. Remember that? If your projection vector pointed in the opposite direction, you could have a negative component. So take the magnitude of that. Now, you could just do this, like get the normal, dot it with B, divide by the magnitude of N. Or if you like formulas, here's the formula. I like this because it makes most sense to me that, what am I doing? I'm finding the magnitude of the component. Here's the component formula. We've done that before, so why go try and do all that? Find the shortest distance between these two parallel planes. So now we have two parallel planes, right? These are parallel. These are parallel, right? Doesn't matter. The shortest distance between them. So if we have the roof and the floor, the shortest distance is just straight down, isn't it? But if we tilt things, again, the shortest distance is not straight down on these two. It's at the same angle as the normals, isn't it? So how would you recommend we do this? Okay. Okay. I'm with you. We have two planes, right? I'm just going to draw them. Here's one plane. Here's another plane. The formula I just gave you was the shortest distance from a point to a plane, right? A point to a plane. Well, why don't we just pick any point we want on this second plane, right? Any point, or on the top plane. Then we're trying to find the shortest distance down to this plane, right? So we can really just kind of scrap that first plane now, right? And now we're back to what we're what the formula was. So I'm going to need to create a vector. So picking a point on the other plane, creating this vector, getting the normal vector, and doing the component of the b onto the n. So let's just make up the numbers. The first vector, I'm out of time. I don't have time to do this, sorry. Let me hand out your take-home quiz. Let's do a week from today. I would like to talk about this real quick because I want to tell you what you can and can't do. Allie? Yeah. Sure. That's all right. Take these and pass them back. It's just one page. Everyone have it? Got some? Okay, real quick, due at the beginning of class on Monday. Oh, wait, that should say 9:15. Is that 15th is Monday, right? Okay, oops, that's 9:15. Beginning of class, do 4 of the 5 problems. You can do all 5, but you turn in that 5th one as bonus on a separate page, separate paper, all right? You must show all steps, justify all answers. Your work must be neat, in order and stapled. Box your final answers where appropriate. Sometimes you can't. All these problems should be done using concepts from Chapter 10. So, look, first one, find the equation of a plane. So, for a plane, what do you need? 2 vectors and a point. Or you could just say you need a point and a normal vector, right? Number 2, find the equation of a line. Okay, what do you need for the equation of a line? Point and direction vector, right? Number 3, find the shortest distance from the center of a quadratic surface. The center of a quadratic surface is really a what? If I have some quadratic surface, we haven't talked about them, but center of a sphere is a what? The center of a sphere is a what? A point, right? So I'm saying find the shortest distance from some point to what? The line of intersection of 2 planes. Well, we haven't figured out how to find the shortest distance between a point and a line yet. That's next class. We couldn't do that. So right now, you should be able to do number 1 and 2. Numbers 1 and 2 for sure you could do. By the end of next class, you'll be able to do 3, 4, and 5. All right. We're good. Homework out of this. Is there a homework assignment at the back of this? These notes? No? If you've just been kind of coasting along and not really doing your homework and still getting by okay, this section for sure you need to take a look at for homework. I would recommend on the homework for this is page 72, 572. 1 through 11 and 15. 1 through 17 odd, and then 21 through 37 odd. It's a lot of work. It's a lot of work right there. You can't do all of this yet, all right? But at least it'll give you a place to start. And there's more homework that I might add to that. Yeah, later. All right. Have a good day. I need to look through them all. No, not all of them. Not all of them. The first 1 through 17 odd you should be okay with. Sure. Let me turn off my recording and stuff real quick.